Hey everybody, welcome back to another chemistry lesson. Today we're going to talk about gases and the kinetic molecular theory. So gases are composed of particles that are moving around really fast in their containers, and they do move in straight lines until they come into contact with a container or another gas particle or something like that. Whenever they have a collision, they change directions. But there is a lot of empty space in between the gas particles, which is how they have the freedom of movement and how they get some of their properties. So things that we know about gases are that they expand to completely fill their container. They take the shape of their container. They are low density, which is much less than a solid or a liquid, which is why it's see-through. Right? There's a whole lot of matter in between me and the camera, but you can still see me because there's so much empty space. Again, because of that empty space, gases are compressible, and mixtures of gases are always homogeneous fluids because there's all this random motion. The gas particles are constantly mixing each other so that there is a uniform distribution of everything in a mixture. So the kinetic molecular theory is the simplest model for discussing the behavior of gases. So in this theory, a gas is modeled as a collection of particles, either molecules or atoms, depending on the gases, that are in constant motion. We know this is true. But there's a little bit of nuance to this, right? Our particles are moving constantly. The assumption is that the attraction between particles is negligible, and this is mostly true because there is so much space in between them, they can't be attracted to each other across that distance. Then, when moving gas particles hit other gas particles or the container, they don't stick to each other. They bounce off and continue moving in another direction, and there's a lot of empty space between them compared to the size of the particles. Now, the average kinetic energy of the gas particles is higher in gases than it is in the same substances, solid or liquid phase. And this is directly proportional to the temperature in Kelvin. As we raise the temperature of the gas, the average speed of the particles increases, and this is where we get our temperature by definition. It is important to know that not all of the particles are moving at the same speed, but the average speed increases as we increase the temperature of our gas. Now, the collisions between particles with each other or particles with their container walls are assumed to be completely elastic. So what that means is, when they collide with each other, they can exchange energy, but there is no overall loss of energy. Any kinetic energy lost by one particle is completely gained by the other. And this is where it's not exactly true, but it's an assumption we have to make in order to be able to talk about gases. Okay? So, what the heck is an elastic collision? It's kind of like when you have two billiard balls that hit each other. So we've got these two really solid balls that hit each other. And basically, you can have one that's sitting still, one that's moving. And when the moving one hits it, it can pass all of its energy on to the one that was sitting still. And now it's sitting still and the other one's moving, right? An inelastic collision is any collision where we're losing some of the energy associated with it as heat. Or there's, not a transfer. I can't think of anything else at the moment. But we're losing some of the energy. So an example here is we have two lumps of clay, let's say, that squish together, right? Another example of an inelastic collision would be if I were to kick a soccer ball against a concrete wall, right? That soccer ball, when it makes contact, it doesn't go boink, right? It sort of smushes. If you've ever seen a slow motion video of a ball hitting a wall or something like that, it squishes. that squish allows some of that energy to be lost as heat. It may not be a lot of it. It may come back off the wall super hard, just like it went on there, but there is some loss as heat. So that would be an inelastic collision. Another example of an inelastic collision would be a car accident, right? Cars are designed to crumple because that crumple takes some of the energy that's in that collision and distributes it to the parts of the car as they crumple, rather than to you as the person inside the car. So even though we're talking about gas particles, there is a little bit of this going on, but we operate under this assumption. Okay? All right, so now where does pressure come from? The pressure is the force exerted per unit area by gas molecules as they hit the surfaces around them. So the amount of gas pressure in your car tire, for example, comes from the air particles in the tire hitting the side of the tire. So that's why you have to have a certain amount of tire pressure in order for your car to drive well, because it keeps the tire inflated, right? If the particles are hitting hard enough, it keeps the tire inflated versus letting the tire sort of squish, right? So just as a ball exerts a force when it bounces against a wall, a gaseous atom or molecule also does that. And so there's a formula for that. Pressure is equal to the amount of force that's being applied over the area, so square footage, so to speak, that it's being applied to. So because gas particles are constantly moving, they're always hitting the sides of their containers everywhere they go. And so we have a lot of gas particles exerting force on the surface around them, and so the pressure is constant. Even though the gas particles may not all be moving at the same speed, on average, their speed is the same, so we're going to have about the same amount of force at all times being applied, because this gas particle bounces and then comes off, and while it's not bouncing, this one is bouncing, and then while it's not bouncing, this one is bouncing. So we get this constant pressure. That's where that comes from. So our gas pressure is the result of molecular collisions. And when we have more collisions, we have more pressure, right? This is where several factors come into play. The number of gas particles in a given volume. So if I am, again, let's think about a car tire. Whenever my tire is going flat, what do? I put more air into the tire. So if I have more particles, I have more collisions, more pressure. Right? This also matters with the volume of the container. If you've ever taken I don't have one with me, but a plastic water bottle that's a little bit squishy, if you twist the water bottle, what you're doing is reducing I'm sure you've all done it, where you do that and then you can and like shoot off the cap. Everybody did it in elementary school at my school, so hopefully you've all had that experience. But what you're doing is you are literally reducing the volume of the bottle by twisting the bottle. When you reduce the volume of the container, you have the same number of particles in a smaller amount of space. So our gas pressure depends on the amount of space that we have in the container, the volume, and it also depends on the average speed of the gas particles. Remember that the higher the temperature, the higher the average speed, the higher the pressure. So higher temperature of the same gas sample will give you a higher pressure. Now, our total pressure depends on several factors, which includes the concentration of gas molecules. So that's just molecules per volume, right? The higher the concentration, the greater the pressure. As volume increases, what that means is we have fewer gas molecules per volume, right? Our number of molecules doesn't change, but since our volume is increasing, the concentration is going down, which means fewer collisions, lower pressure. Okay, so why do we care about pressure? What does that do for us in everyday life? Well, let me tell you. It affects our weather. So variation in the pressure in different locations on Earth's surface creates wind, and it also creates weather systems. So high areas of high pressure are indicated on maps like this with an H. Areas of low pressure are indicated with an L. Usually high pressure is associated with clear weather, good weather. These are the good weather days. And then low pressure is usually associated with unstable or bad weather. And that's what this looks like on a map. Now, the number of gas particles in a given volume also will decrease with increasing altitude. So in addition to just weather patterns, if you are going up a mountain, you're also going to experience a change in pressure because our number of gas particles decreases the further up we go. Less gas per area means lower concentration, lower pressure. Now, pressure exerted by a gas is dependent on the number of gas particles in that volume. So the fewer gas particles, the lower the amount of force per unit area. A low density of gas particles results in low pressure. A high density of gas particles results in high pressure. Hopefully that's pretty common sense at this point. All right. Another place that you may experience, hopefully not, gas pressure is in the ear. So if there is a difference in pressure across your eardrum, you can rupture your eardrum, which hurts really bad. It feels like you're being stabbed in the head with a knife. But this is why when you are in an airplane, especially if you've had a cold or some sort of congestion, if you're in an airplane, your ear might hurt because what you're getting is uneven pressure on either side. So here, this is an example of what you may experience if you are in an airplane or if you drive up a mountain, for example. You have this reduced external pressure and then the normal pressure that was established on the inside of your eardrum. This happens in the opposite direction if you dive to the bottom of a swimming pool, for example, while holding your breath. If you do that, you're going to have this increased pressure on the outside pushing in on your eardrum. Either way, if that difference in pressure is too great, you can rupture your eardrum, which is not something you want to do. 0 out of 10, do not recommend. All right, so we can measure pressure using a manometer. The pressure is measured with, basically we trap gas in this piece of glassware. Manometers are U-shaped that are partially filled with liquid, and it's connected to a gas sample on one side and then open to the air on the other side. So what we get is kind of a tug of war between the external air pressure and then the pressure of the gas that's been trapped inside of the manometer. And so the difference in the level of the liquid can tell you the pressure difference between the gas that's been trapped and atmospheric pressure. So this is what that looks like. We have this high pressure gas here. This is probably mercury. Yes, it's mercury. This is mercury. And so we have a specific gas here. If atmospheric pressure is less than this pressure, which is what's happening here, we get this height difference, and that tells us the difference in pressure. Likewise, it can go the other direction. And if our atmospheric pressure is greater, if we have a high pressure system, it's going to push down, and that instead of being this way, we're going to shift this way. And we can still measure that height difference to tell us the pressure difference. One other place, and especially if you are going into the healthcare field, you're going to see this a lot. One other place that we talk about pressure is with blood pressure. So blood pressure is the force of the fluid that's in your arteries pushing out on the sides of your blood vessels, right? Blood pressure is measured with a sphygmomanometer, I always mess that word up, which is that blood pressure cuff right here. And all you're doing is creating air pressure within the cuff. That's what the little pumpy dude's for. You inflate it with air pressure, and then you can tell what the pressure is based on what you're hearing according to the difference between the fluid pressure in your blood vessels and the air pressure in the cuff. It's very complicated. You don't have to know all the logic behind it all to actually use one. But that's what we're doing, is we are creating that competition, so to speak, and then reading it to give us our blood pressures.